Look up tonight. Go outside, tilt your head back, and look at the sky. You will see darkness, with a few thousand tiny points of light scattered across it. It feels normal. It feels like it has always been this way, and always will be this way. But here is the problem. If the universe is infinite, and if it is filled evenly with stars, then the math says that should be physically impossible. The night sky should not be dark at all. It should be a solid wall of fire. Every single point you look at, in every direction, without exception, should eventually hit the surface of a star, which means the whole sky, from horizon to horizon, should glow as bright as the surface of the sun. Brighter, actually, because you would be looking at infinite suns stacked behind each other in every direction you turn your eyes. So why aren't we all blind right now? Why is the sky dark at all? That question sounds almost childish, the kind of thing a 5-year-old might ask, and then forget about by breakfast. But it is one of the strangest and most quietly profound puzzles in the history of science, and the answer to it is one of the only pieces of evidence you can get just by stepping outside your house and looking up, that tells you, beyond doubt, that the universe itself had a beginning. Let's slow down because the setup to this problem is almost too simple to feel dangerous. Imagine you are standing in the middle of a forest. Not a small forest, an endless one. Trees in every direction as far as you can imagine, stretching out forever with no edge. Now look straight ahead. Your line of sight travels forward, and somewhere out there, close or far, it is going to hit a tree trunk. There is no way to avoid it. No matter which direction you turn, near or far, your eyes are going to land on wood eventually. If the forest goes on forever, then every single line of sight you could possibly draw from where you stand ends on a tree. There are no gaps. There is no direction where your eyes can sneak through to open sky beyond the trees, because there is no beyond. It's trees all the way out, infinitely. Now replace the trees with stars. If the universe is infinite in size, and stars are scattered through it at roughly the same density everywhere, the same logic applies. Pick any direction. Look along that line. Somewhere along that line, sooner or later, your gaze is going to land on the surface of a star. Not empty space behind it, a star. And if that is true for one direction, it is true for every direction, because there is nothing special about any one direction in an infinite universe. Which means the entire sky, every single point of it, should be covered edge to edge with starlight. Not a few dots scattered on black. A continuous, unbroken sheet of starlight, with no gaps anywhere. Because every gap, every dark patch, is just a spot where your eyes haven't reached the next tree yet, or in this case, the next star. And starlight up close is not gentle. The surface of a star is blisteringly bright. So if your eyes, wherever you point them, are always resting on some star's surface, that means the entire sky should be glowing with the brightness of a stellar surface. Not the soft brightness of a faraway twinkle, the raw brightness of standing far too close to a furnace. The whole sky, in every direction, should look roughly as bright as staring directly at the sun. Day and night would stop being meaningfully different, because the night sky itself would be a second sun wrapped completely around you, in every direction, all the time. That is obviously not what we see. And that gap, between what simple logic predicts and what we actually observe with our own eyes, is the heart of the problem. It is not a small inconsistency you can wave away. It is night and day, literally. The universe, on paper, demands a sky on fire. Reality hands us a sky that is mostly black, with scattered pinpricks of light so faint you can blot one out with a fingertip held at arm's length. Something, somewhere, has to be wrong. Either the universe isn't actually infinite and uniformly filled with stars the way we assumed, or there's some mechanism quietly protecting us from the apocalyptic brightness the math demands. And figuring out which one it is, and why, took some of the sharpest minds in the history of astronomy a few centuries to actually nail down. This isn't some fringe idea that a modern science channel invented to get clicks. People noticed this was strange a very long time ago. The astronomer Johannes Kepler was already wrestling with a version of it in the early 1600s, using the darkness of the night sky as an argument that the universe could not be infinite, because an infinite universe should produce infinite light. 2 centuries later, in 1823, a German astronomer named Heinrich Wilhelm Olbers wrote about the problem so clearly and so thoroughly that it eventually got named after him, Olbers' paradox. Not because he invented the puzzle, but because he forced people to actually sit with it and admit that something about their picture of the cosmos had to be incomplete. Here is a detail that tends to surprise people. One of the clearest early descriptions of the actual correct solution didn't come from a professional astronomer at all. It came from the writer Edgar Allan Poe in a strange, sprawling prose essay he published in 1848 called Eureka. Buried inside pages of dense, almost poetic speculation about the cosmos, Poe reasoned that if the universe really were infinite and uniformly scattered with stars, the gaps between them should eventually be filled in completely by starlight from ever more distant stars. Exactly the wall of fire problem we've been describing. And then he proposed that the only reason we don't actually see that wall of fire is that light from the most distant stars simply has not had time to reach us yet, because the universe has a finite age, and light only travels so fast. A poet, writing decades before this was demonstrated through careful observation, landed almost exactly on the modern resolution to the puzzle, just from thinking carefully about light, time, and distance. That should tell you this problem rewards patient logical thinking just as much as it rewards advanced mathematics. This sat as a genuine, respected problem in the history of physics for generations afterward, discussed by people who fully understood the mathematics of gravity and optics, and who still couldn't immediately prove why their equations were predicting a blinding sky that clearly didn't exist. That should tell you something. This is not a trick question with an obvious answer. It is a real fracture between theory and observation, and chasing that fracture down leads somewhere genuinely strange. So let's actually look at why the math is so stubborn about this. Because the first instinct most people have is, well, obviously distant stars are dimmer, so far away starlight just fades out, and that's why the sky isn't bright. It sounds reasonable. It is also, mathematically, dead wrong. And the reason why is worth walking through slowly, because it's beautiful in a slightly unsettling way. Picture the universe sliced into thin spherical shells around you, like the layers of an onion, each one a little farther out than the last. Take one shell, say between 100 light-years and 101 light-years away. Now take a second shell, much farther out, between 1 million light-years and 1,000,001 light-years away. The second shell is obviously much, much bigger than the first one. Its surface area is enormous compared to the close one, because surface area of a sphere grows with the square of its radius. So that distant shell contains vastly more stars than the close one, packed across a much larger area. Here's the part that breaks people's intuition. Each individual star in that distant shell does look dimmer to you, because brightness fades with distance, specifically with the square of the distance, following something called the inverse square law. A star twice as far away looks 1/4 as bright. A star 10 times as far away looks 100 times dimmer. That part matches intuition just fine. But watch what happens when you put those two facts together. The number of stars in a shell grows with the square of the distance. The brightness of each individual star fades with the square of the distance. One of those is growing exactly as fast as the other one is shrinking. They cancel out perfectly, which means every single shell, no matter how far away it is, contributes exactly the same total amount of light to your sky as every other shell of the same thickness. The close shell and the impossibly distant shell contribute identical amounts of total brightness. Distance, by itself, does not dim the overall picture at all. It only redistributes the same brightness onto a thinner-looking, more spread-out band of stars per unit area, while there are proportionally more of them. Now, if the universe is infinite, you have an infinite number of these shells, stacked one after another, going out forever. And if each shell contributes the same non-zero amount of light as every other shell, then adding up infinitely many of them gives you an infinite amount of total light hitting your eyes. Not a lot of light, infinite light. That is the mathematical gut punch hiding inside Olber's paradox. It is not solved by saying, but far things are dimmer, because the math already accounts for that, and the dimming is exactly canceled out by the sheer growing number of things out there. Distance does not save the night. It cannot save the night. Not in an infinite, uniformly star-filled universe, because the geometry is rigged from the start to cancel out the fading. This is where people often reach for a second intuitive fix. Maybe it's not distance that blocks the light. Maybe it's something physically in the way. Dust, gas, clouds of cosmic material drifting between the stars, soaking up starlight before it reaches us, like fog blocking out a row of streetlights. It feels like a satisfying answer because we know interstellar dust is real, and we know thick clouds of gas absolutely do block visible light from stars behind them. Nebulae photographed by telescopes show exactly this kind of light-blocking effect. So maybe that's it. Maybe a thin haze of cosmic dust, spread throughout an otherwise infinite universe, quietly absorbs almost all of that theoretically infinite starlight before it ever gets to Earth. And that's why the sky looks dark instead of blinding. This explanation has a fatal flaw, and it's a thermodynamic one. Dust doesn't make light disappear. It absorbs light, which means it absorbs energy, which means it heats up. And an object that heats up starts to glow and re-emit energy of its own, just usually at a different wavelength than what it absorbed, often shifting visible light into infrared heat radiation. Think about a black car left out in the sun all day. The paint absorbs visible sunlight, and within an hour the dashboard is radiating that absorbed energy back out as heat you can feel with your hand the moment you open the door. The car doesn't store that sunlight forever. It reaches some equilibrium temperature and keeps shedding the energy it takes in, for as long as the sun keeps shining on it. Cosmic dust behaves the same way, just on a much grander scale and over a much longer clock. Here is the killer detail. If this dust has been sitting in an infinite, eternal universe, bathed by infinite incoming starlight for an infinite amount of time, it doesn't just absorb a little heat and stay cool the way your car cools off again at night. Given truly infinite time, with no night to cool off in, that dust would keep absorbing energy until it reached thermal equilibrium with the stars themselves. It would heat up and up and up, until it was just as hot and just as bright as the stars whose light it was supposedly blocking. At that point, the dust itself becomes another source of blinding light, and you're right back to a sky on fire, just glowing from dust instead of directly from stars. Dust doesn't escape the paradox. Given enough time, it just becomes part of the problem. It makes the puzzle worse, not better. Because now you'd need to explain why the dust itself isn't glowing white-hot too. So neither distance nor dust gets us out of this on their own. The math is airtight as long as you accept the two starting assumptions. A universe that is infinite in size, and a universe that is infinite in age. Eternal, unchanging, the same yesterday, today, and a trillion years from now. Those two assumptions, infinite space and infinite static time, are the real trap here. They feel like harmless, almost obvious things to assume about a vast cosmos. Of course it goes on forever. Of course it's always existed. Why wouldn't it? But once you accept both of those assumptions together, the blinding sky isn't a possibility. It's a mathematical certainty. You don't get to keep an infinite, eternal, uniformly populated universe and also get a dark night sky. Something in that pair of assumptions has to give. And this is exactly where modern cosmology kicks the legs out from under the puzzle, because it turns out one of those two assumptions is simply false. The universe is not infinitely old. It has a finite age. Based on decades of careful measurement, our best current estimate puts the age of the universe at around 13.8 billion years, give or take a small margin of error. That number changes everything about this problem because of one simple, almost embarrassingly basic fact about how light actually behaves. It travels at a finite speed, fast as it is, and it takes time to cross distance. Here's what that means in practice. Light from the sun takes about 8 minutes to reach Earth. Light from the next nearest star takes a little over 4 years. Light from the center of our galaxy takes around 26,000 years to reach us. Light from the most distant galaxies we can detect has been traveling for over 13 billion years just to arrive here, right now, tonight. So when you look at any object in the sky, you are never seeing it as it is right now. You are seeing it as it was, however long ago its light left it on its journey toward your eyes. Now stretch that idea to its logical limit. If the universe is only about 13.8 billion years old, then there is a hard ceiling on how far away any light source could possibly be, and still have had time to reach us. Light from a galaxy 15 billion light-years away simply has not had enough time to arrive yet, because the universe hasn't been around long enough for that journey to be completed. That creates something astronomers call the observable universe, a finite bubble centered on us, bounded by a cosmic horizon, beyond which there might be more universe, possibly infinite more universe, but none of its light has reached us yet. And by definition, none of it ever can have reached us yet, given how young everything still is. Think of it like standing on a beach at night, watching for the lights of ships out on the ocean. The Earth curves away from you, and past a certain distance, the curvature of the planet physically blocks your line of sight to anything beyond that point, no matter how powerful the ship's lights are. There could be an entire fleet of brilliantly lit ships glowing just past your visual horizon, and you would never know it. Not because the light doesn't exist, but because the horizon itself prevents it from reaching your eyes. The cosmic horizon works in a conceptually similar way, except instead of curvature blocking your view, it's simply a matter of time. Light beyond a certain distance hasn't had enough time since the universe began to cross the gap and reach you. It's not blocked, it just hasn't arrived yet. And it can't have arrived yet, no matter how patiently you wait one more night, because the math of how old everything is sets a hard limit. This single fact single-handedly demolishes the original argument behind Olber's paradox. Remember, the paradox needed infinitely many shells of stars, stacked outward forever, each contributing equal brightness, adding up to infinite light. But if there's a horizon, a cosmic edge to what we can currently see, then there is no longer an infinite number of contributing shells. There's a finite number. The summation stops. You add up shell after shell of starlight, and instead of marching toward infinity, the total brightness caps out at some large but completely finite value. Because past the horizon, there simply isn't any arrived light yet to add into the total. A finite number of finite contributions gives you a finite answer, not a blinding inferno. The forest, it turns out, does have an edge after all. Not a physical edge where the trees stop, but a kind of veil of darkness imposed by time itself, beyond which no light has had the chance to reach us, regardless of how many stars might be standing out there in the dark. But here's where the story gets even stranger. Because solving the infinite shells problem with a finite horizon doesn't fully explain everything we see when we actually study the sky carefully. There's a second piece to this, and it involves the fact that the universe is not just old and finite, it is also expanding. And that expansion does something deeply strange to light that travels across cosmic distances for billions of years. Picture stretching a long rubber band with a wavy line drawn across it in marker. As you pull the ends of the rubber band apart, That wavy line gets stretched out too, the peaks and troughs of the wave spreading farther apart from each other. Light behaves in an analogous way as it travels through expanding space. Space itself, the fabric the light is moving through, is stretching as the universe expands, and that stretching pulls the light's wavelength longer and longer the farther it travels and the longer it's been in transit. Longer wavelength light sits lower down the spectrum, shifted toward the red end of visible light, and if it gets stretched enough, it slides entirely out of the visible range altogether, first into infrared, then further down into microwave wavelengths that human eyes cannot detect at all. Astronomers call this redshift, and the more ancient and more distant the light, the more dramatically it has been redshifted by the expansion it traveled through to reach us. This matters enormously for our puzzle, because it means that even within our cosmic horizon, even among the finite amount of light that has had time to arrive, a huge amount of the most ancient light has been stretched completely out of the range our eyes can perceive. It hasn't vanished. It hasn't been blocked or absorbed. It's still out there, still arriving, just no longer in a form your retinas can register as visible brightness. The universe is quietly converting old starlight into a wavelength your eyes are blind to, simply through the geometry of its own ongoing expansion. And there is one extraordinary, very real example of exactly this happening, on a scale that covers the entire sky. Go back to a time not long after the universe began, when everything was compressed into an extremely hot, extremely dense state. In its first few 100,000 years, the universe was so hot that matter existed as a dense plasma, and that plasma was so thick and energetic that light could not travel freely through it, constantly scattering off charged particles the way light scatters inside a thick fog. Roughly 380,000 years after the beginning, the universe finally cooled enough for electrons and protons to combine into neutral atoms, and the instant that happened, the fog lifted. Light was suddenly free to travel in straight lines without constantly bouncing off charged particles. That moment released an enormous, universe-filling flash of light, radiating in absolutely every direction, everywhere, all at once. If you had been standing anywhere in that early universe at that moment, you would have been surrounded by a sky genuinely as bright and blinding as the surface of the sun, in every direction, exactly the kind of sky Olber's paradox originally predicted. That light never stopped traveling. It has been crossing the universe for the entire 13.8 billion years since that moment, and the universe itself has been expanding the whole time it traveled. By the time that primordial flash of blinding light reaches us today, the expansion of space has stretched its wavelength by an almost unbelievable factor, dragging it from blistering visible and ultraviolet light all the way down into the microwave portion of the spectrum. We call it the cosmic microwave background, and it really is there, filling the entire sky, in every direction you look, with shockingly uniform intensity, exactly as the old fiery argument predicted it should be. The blinding wall of light Olber's paradox demanded genuinely existed, once, everywhere. It just got stretched by billions of years of cosmic expansion into a faint microwave hiss, with a temperature of about 2.7 degrees above absolute zero, completely invisible to human eyes, detectable only with radio antennas tuned to exactly the right frequency. The story of how this leftover glow was actually discovered is almost too fitting. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working with a large, extremely sensitive antenna in New Jersey, originally built for satellite communication, and they kept picking up a faint, constant hiss of microwave static, no matter which direction they pointed the antenna. It didn't change with the time of day. It didn't change with the season. They checked every possible source of interference they could think of, including, famously, cleaning out pigeon droppings that had built up inside the antenna horn, suspecting the birds might somehow be responsible for the noise. None of it explained the signal. What they had stumbled onto, almost by accident, was the afterglow of the early universe itself. That ancient, once blinding light, now stretched into a faint microwave murmur surrounding the Earth from every direction at once. They later received the Nobel Prize for what is, in a real sense, the universe's oldest surviving photograph, hiding in plain sight in a piece of communications equipment nobody had built to look for it. So, in a strange way, the night sky isn't actually dark in every sense. It is dark to your eyes, because your eyes can only register a narrow sliver of the full electromagnetic spectrum, the part we call visible light. But point a microwave-sensitive instrument at any patch of sky, day or night, and you will pick up that same ancient afterglow, almost perfectly uniform, coming from literally every direction at once, just as the original argument insisted it must. The fire never disappeared. It got stretched into a key your eyes simply cannot turn. Put these two resolutions together, and the entire paradox collapses cleanly. First, the universe has a finite age, which means there is a cosmic horizon, a boundary past which no light has yet had time to reach us, which caps the otherwise infinite sum of starlight at some large but completely finite number, rather than letting it run away toward infinity. Second, even the light that has reached us from extremely ancient, extremely distant sources has been redshifted by the ongoing expansion of space, stretched out of visible wavelengths and into bands our eyes can't see, draining away the apparent brightness of the very oldest and most abundant light in the cosmos. Combine a horizon that limits how much light has had time to arrive with an expansion that dims and shifts whatever light does arrive. And instead of a sky screaming with the brightness of infinite stacked stars, you get exactly what we actually observe: scattered points of starlight bright enough to notice individually, set against a background that is overwhelmingly, restfully dark to our eyes, while still secretly glowing with ancient radiation in wavelengths we need instruments to detect. It's worth pausing on how strange it is that the night sky is dark, but not empty in this way. To your eyes, most of the sky between the stars looks like simple blank blackness, nothing there at all. But that apparent emptiness is an illusion created by the limits of human vision. Fill in the picture with radio telescopes, microwave detectors, infrared sensors, and X-ray instruments, and that supposedly empty blackness turns out to be humming with structure. The leftover glow from the early universe, the radio chatter of distant galaxies, high energy bursts from collapsing stars, faint infrared warmth from clouds of dust and gas. The night sky's darkness is not an absence of activity. It's a narrow window. Your eyes are tuned to perceive only a thin slice of everything that's actually happening up there, and the dark gaps between the stars are simply regions where nothing happens to be glowing in that one particular, narrow band of light your retinas are built to detect. There's also a more down-to-earth piece of the puzzle that's worth mentioning, separate from horizons and redshift, just to round out the picture. Even setting aside the limits imposed by the age of the universe, the raw density of stars actually out there, within the volume we can currently observe, simply isn't high enough to tile every line of sight with a star's surface in visible light, the way the original infinite forest argument assumed. Stars are mind-bendingly far apart relative to their own size. If you shrank the sun down to the size of a basketball, the nearest star to it on that same scale would be sitting more than 1,000 miles away, with almost nothing but empty space in between. Multiply that out across the actual finite size of our observable universe, and you get nowhere near enough stars, packed densely enough, to physically intercept every random line of sight you could draw outward from Earth. There are simply still gaps, lots of them. Lines of sight that slip between every star without striking one within the time light has had to reach us. So even before you factor in horizons and redshift, the sheer thinness of how spread out stars really are, compared to the size of the currently observable universe, already leaves plenty of room for genuinely empty-looking gaps between the visible points of light in the sky. Now step back and look at the whole shape of this argument, because the conclusion it leads to is genuinely remarkable, and it's the kind of thing that's easy to walk past without noticing how big it actually is. The darkness of the night sky isn't just a pretty backdrop for stargazing. It is direct, physical, observable evidence, available to literally anyone who walks outside and looks up, that the universe cannot be both infinite in extent and infinite in age, sitting there static and unchanging forever. If it were truly infinite and eternal in that classical sense, the math is unforgiving. The sky would have to be uniformly, blindingly bright, every night, forever, with no exceptions. Since it obviously isn't, since you can step outside right now and see a mostly dark sky with scattered stars, you are looking directly at proof that the universe had a beginning, a finite age, a starting point in time, sometime around 13.8 billion years ago, before which the kind of starlight-filled cosmos we live in didn't yet exist in its current form. That is an almost unbelievable amount of cosmological information packed into something as ordinary as a dark sky on an ordinary night. You don't need a particle accelerator. You don't need a space telescope. You don't even need a backyard telescope. You just need your own eyes, a basic understanding of geometry and the speed of light, and the willingness to ask an obvious-sounding question that turns out to have an enormous answer hiding underneath it. Why isn't the sky on fire? The answer threads together the finite age of everything that exists, the literal speed limit on how fast information and light can travel, and the ongoing stretching of space itself, all converging on the same conclusion from completely different angles. The universe began. It is still young, relatively speaking, even after nearly 14 billion years. And the comforting darkness you see overhead every night is not the universe hiding something from you. It's the universe quietly showing you, in the most direct way imaginable, exactly how old it actually is. So the next time you step outside at night and look up at that familiar, dark, star-dotted sky, you're not just looking at a pretty view. You're looking at the absence of an infinite, eternal universe, an absence so total and so obvious that astronomers couldn't fully explain it for centuries. You're looking at proof that somewhere around 13.8 billion years ago, something happened. A beginning. A moment after which the light we now see slowly began its long journey toward your eyes. Every dark patch between the stars marks a place where light simply hasn't had time to arrive yet, or has been stretched into invisibility along the way. The night sky isn't dark because the universe ran out of stars. It's dark because the universe, vast as it feels, is still relatively young, still finite, still very much in the middle of its story. And the blackness above you is the clearest fingerprint of that beginning you will ever get to see with nothing more than your own two eyes.